Suck, squeeze, bang, blow. That's all you need to know. Are we sure this is the right script? You won't believe me when I tell you this, but jet engines are an incredibly simple design. They basically have one moving part. And yes, that's an exaggeration, but not by much. A jet engine basically has a fan at one end and a turbine at the other, and they're connected by a single rod right down the middle. So when the turbine turns, the fan has to turn because, again, it's all on one rod. It's one moving part. The only question here is, well, what on earth is a turbine? A turbine is just a fan, except it's backwards. So a fan blows something, a turbine is blown by something. This setup is used because you want the fan turned on if you want to move some air along. And the turbine is used if you've got a moving fluid and you want to take energy out of it and use it to do some work. So in a hydroelectric power plant, for example, we have all this water that's held up behind a dam. It's under enormous pressure. And as it comes out of the dam, there's a turbine. And all that energy from the water rushing out makes the turbine rotate and we can generate electricity. In a jet engine, the only thing that we need the turbine to rotate for is so that it can turn the fan at the front. This leaves the rather obvious question of what happens in the middle. The first thing that happens is that the air that's brought in by the fan at the front gets compressed. Normally when we talk about something that needs compressed air, we have to have an air compressor. In a jet engine, not so, at least not per se. Behind the fan that takes air in at the front of the engine, there are a series of smaller and smaller fans, and those compress the air. There's actually sort of a conical structure, although it's on its side, and this conical structure, this cone, gets bigger as it goes back into the engine. And the fans that are built around that get smaller and smaller and smaller. So they're little rings of fans with a big hub at the center. But notwithstanding the geometry, it's just a series of smaller and smaller fans that force the air into a more compact volume of space. Well, when the air gets compact, it also gets hot. So you have the fan at the front, you have a series of ring-shaped fans that compress the air as it moves backwards, it gets dense and it gets hot. Well, what happens next? We spray jet fuel into it and then we ignite it. That's really all there is. As this ignited, hot, dense mix of air and jet fuel explodes, it goes out the back of the engine, and that creates thrust, which makes the engine, and hopefully the airplane to which it's attached, go forward. But at the same time, you're jetting all of this energy out the back of the engine, so you have it go through the turbine. But remember, that turbine is connected to the fan at the front. So it turning really quickly turns the fan really quickly, which sucks more air in. And better yet, all the little compressor sections that were just described, they're on that same single spool. So the whole thing is basically one big moving part. The fan, the compressors, the turbine, it all just spins and it's all attached to one rod at the center. This single spool setup is autocatalytic. That means it's self-sustaining. And that's one of the things that makes jet engines so reliable. The other thing that's cool about the autocatalytic nature of a jet engine is that it doesn't need spark plugs. So in your car, for example, in an internal combustion engine, you have to have things timed very precisely. There are cylinders that go up and down, and you only want a spark to ignite the compressed mix of air and gasoline, in the case of a car engine, when it's under maximum compression. And it's that spark going off that ignites that mix that forces the cylinder to move, and that's how you make your car go. In a jet engine, what we basically have is a cigarette lighter. So if you picture a cigarette lighter, when you first start it, there's a spark, but after that spark is done, the thing simply keeps going. There's a steady supply of fuel coming out, and that fuel is just ignited by the fact that there's a flame sitting right on top of it. And as long as you keep your finger on the switch, the cigarette lighter stays lit, unless someone comes along and blows it out. The same exact thing is true of a jet engine. There's no timing, there's no spark plug that has to fire at just the right second. There are igniters, and those get the whole thing started in the first place, but once it's going, it keeps going. So, fan at the front sucks air in, series of smaller fans compress the air into a hot, dense, small volume. We then spray jet fuel in, and then we ignite it, and it explodes out the back. But once that process is started, the only thing that's igniting the continued flow of jet fuel and air as it goes back through the engine is the fact that it's already ignited one millimeter ahead or 1 millimeter further back in the engine. It's just like a cigarette lighter. The only thing that's igniting the fuel is the fact that there's already ignited fuel there. That's the basic jet engine, and that's true of any jet engine that's out there today, but that's not the type of engine that you'll see if you go to the airport today and get on a plane. What I've described so far is what we would call a turbojet engine. It's got a turbine and it has a jet, so it's a turbojet. But the type of engines that are in use today are called turbofans, and the name is appropriate. At some point, somebody said, well, hold on a second. If we've got this basically one moving part and it's just spinning around, well, why don't we just slap a really big fan on the front, like a big propeller? So they did. That's what a turbofan engine is. And that's why if you go to the airport today and you look at a jet engine, especially a big jet engine on a really big plane, you'll notice that you can see daylight straight through it. It almost looks like there's nothing in the engine. There are a lot of reasons to do this. In an old-fashioned, we'll call it turbojet engine that didn't have the big fan on the front, all of the thrust came from the exploding mix of hot air and jet fuel going out the back of the engine. In a modern jet engine, more than 80% of the thrust comes from just the big fan. So yeah, there's this hot compressed mix of air and jet fuel and it's exploding out the back, and that does produce some thrust. But most of it just comes from the great big fan spinning around. It's just a big propeller. There are other advantages beyond efficiency to having this big fan on the front of your jet engine. One of them is that it's very quiet. So as you can imagine, when you take compressed air and mix it with jet fuel and then ignite that mixture, it goes bang very loudly. Jet engines are quite noisy. But sound has to propagate through the air. It can't, for example, travel through the vacuum of space. So if you were to take that very noisy jet engine and put a big wash of air flowing over it, those sound waves would propagate out not into the surrounding environment, but into this wash of air that's going backwards over the engine core. And that's what a turbofan does. So you have the basic rudimentary jet engine core, as I've described in this video, and you have the big fan on the front. Well, the air that big fan is pushing through the engine goes mostly around the engine core and takes with it the sound that's being emanated, that's coming out of that very loud, hot section of the engine core. We refer to the current generation of engines as high bypass turbofans. And all that means is that most of the air that's coming through that big fan at the front bypasses that hot engine core section. It just goes right out the back. As described, that's quite useful in reducing the amount of noise that comes out of the engine, but it's also great at keeping the engine cool. Now, in flight, that's not normally a big concern. At 36,000 feet, it's -50 or -60 degrees. It's very cold. But when the plane is on the ground, well, you don't have this wash of freezing cold air going over and through the engine. So an old-fashioned turbojet engine that didn't have the big fan on the front and didn't have most of the air bypassing the combustion section of the engine, well, it would get very hot, and it would be difficult to control that temperature. It'd be difficult to keep it cool because it would just be sitting there on the ground. And if the plane was taxiing for a long time or just stuck on the ground, the engine would experience a much greater range of temperature change than you really want. Well, with a turbofan, you don't have that problem. The hot central section of the engine is always being cooled by this big wash of air that's going past it in a high bypass turbofan, and that air is just coming from the big fan at the front of the engine. I referred to jet engines as having just one moving part, and that is, to be fair, an exaggeration. The main part is that one rotating spool. Well, in order to make engines even more efficient, we now use 2 or 3 spool designs, and all that means is that the big fan on the front is on a different spool. It's on a different rod through the center of the engine and therefore can spin at a different speed. The geometry by which that's set up is clever and relatively simple. So we have the one spool at the center, and it has the, relatively speaking, small fan, the compressors, and the turbine at the back. The air comes in, gets compressed, mixed with jet fuel, explodes out the back, turns the turbine, which turns the little fan. Well, all they've done is put another turbine behind the first one and have a second shaft that runs through the first shaft, and that's connected to the big fan in the front. So as this hot exhaust goes out the back of the engine, it goes through 2 turbines. The first turbine takes the brunt of the explosive force of this constant ignition of fuel and air as it's exhausted out the back of the engine. It picks up a lot of energy from that, spins very quickly, and that turns the fan that's taking air in to be compressed and then mixed with jet fuel and combusted to keep the cycle going. Just behind that is the second turbine. And because it's slightly further away, it gets slightly less energy, although still quite a bit. So it spins slightly more slowly. And that causes the big fan at the front to spin slightly more slowly than the inner section of the engine. But remember, it's a great big fan. So the blade tips on this thing are moving at considerable speed, even though it's rotating at a lower RPM, so to speak, a lower rate of rotations. The circumference is enormous, so these fan blades are whipping around at considerable speed, sometimes greater than the speed of sound. And when we say large, the largest jet engines are more than 10 feet in diameter. Beyond the main purpose of a jet engine, which is to produce thrust and move the airplane forward, there are a bunch of cool little accessories that we sort of tack on the side. Airplanes need electrical power. Fortunately, electrical power is usually generated by spinning something. So we take a generator and we simply stick it on the side of the jet engine. The jet engine has a great big moving part inside of it, and that spins our generator, and voila, we've got lots of electricity. Most airplanes today will have at least 3 of these generators, one on each engine, and then there's another one in the tail. And of course, you've also got batteries, and there are backup systems beyond all that. The other convenient thing about the way jet engines are designed is that they're full of hot air, kind of like some people you might know. If you've ever driven your car in the wintertime or seen videos on YouTube of people who've made the mistake of driving their car in the wintertime, you'll notice that snow and sleet and slush from the ground tends to get accumulated on the front of the car, and for that matter, the rest of the car. It just gets sprayed everywhere and tends to build up. So it seems odd that an airplane can fly through the sky, which is notably where wintry precipitation tends to come from, at hundreds of miles an hour, exposed to sleet and snow and freezing rain, and yet its wings, these giant slabs of metal that stick out into all that, remain perfectly clean. We achieve that through a very clever system that's also quite simple and takes advantage of the basic way that jet engines are built. At the core of the jet engine, we have the fan that takes air in, and then a series of fans that compress the air until it's very hot and very dense. Well, all they do is poke a hole in that compressor section, and they bleed off some of that air. We call that bleed air. Bleed air is taken from the compressor section of the engine, and this is just air that's been smashed down into a small volume, so it's very dense and very hot, and they route it out along the leading edges of the wings. And in those leading edges, there are piccolo tubes, and those are exactly what they sound like. It's just a long tube with little holes in it. So as long as the engine is running, hot air will come out of the compressor section of the engine and be routed out along the wings. The wings will stay nice and warm, and wintry precipitation will not accumulate. By the same token, you might have wondered how it is that if it's negative 50 or negative 60 outside, the airplane cabin itself is nice and cozy and warm. That air that's being bled off of the compressor section of the engine, that bleed air, in addition to going out and warming the wings, it also gets piped into the cabin. Now, it can't just be sent into the cabin straight away. Everybody on board would be baked to death, and that would be unpleasant. Rather, it goes through a series of manifolds and systems that expand it as necessary and mix it to get it down to just the right temperature, and then it goes into the cabin. That's how we get pressurized, warm air in the cabin, even though the pressure outside would kill you if the temperature didn't, at negative 50 or 60 degrees. Incidentally, when this air is being pumped into the cabin, it's sent up to the flight deck under slightly higher pressure than it is the rest of the cabin. And that's done so that if there were to be a fire on board, for example, smoke would be moved back away from the flight deck and into the cabin rather than the other way around. It also ensures that the pilots get the freshest supply of air, and most importantly, ensures that if they have flatulence, it gets swept out of the flight deck and into the cabin.